Hi, this is Dr. John Bergduff. The objective of this function is to graph a rational function defined by an equation consisting of a single simplified fraction. An example of such a function is right here. The function consisting of the polynomial 2x squared plus 7x minus 4 divided by the polynomial x squared minus 4. Now, as you might imagine, given how elaborate the equation is, the graph of a rational function is going to also be pretty elaborate. But fortunately, there's a fairly small set of steps that you can go through to get a rough sketch of a rational function without plotting a great number of points and without a whole lot of difficulty. Let me show you how to do that. There are basically going to be 7 steps. We'll start with the first one. Locate the y-intercept of the graph by letting x equal 0. A point on the y-axis has an x-coordinate of 0, so basically what you do to calculate a y-intercept is to figure out what is f of 0, plugging in 0 for all values of x. And this could probably be done in your head because many of these terms, when you plug in the 0 for x, will just turn out to be 0. In fact, you'll get negative 4 over negative 4, and that tells you that f of 0 is 1, and that is your y-intercept, and you can go ahead and plot that point. That's step 1. Step 2, locate the x-intercepts by factoring the numerator and setting each factor equal to 0. So we're going to take the numerator, and we're going to factor it. Now, I'm going to leave the denominator be for a minute. We'll just kind of leave that alone. We'll come back to that later. To factor the numerator, I'm going to need to use trial and error factoring, like we've done before with factoring trinomials. I need 2 numbers that multiply to give me a 2 in order to reach, in order to reach that 2x squared term in the first term there. 2x times x would probably be just about the only way that can be done. And then I'm also looking for 2 numbers that multiply to give me negative 4 to give me the constant term. And I believe you could see that if you put a plus 4 here and a minus 1 here, you would do it. And you can check that by using the FOIL rule. 2x minus 1 times x plus 4 is equal to 2x squared, that's the first term, plus 8x, that's the outside term, minus x, that's the inside term, minus 4. That will indeed give me 2x squared plus 7x minus 4, exactly what I wanted. So having done that, I locate the x-intercepts by taking each of those factors and setting them equal to 0. And this is going to tell me that there are 2 x-intercepts. One of them is going to be at 1/2, and the other one at negative 4. And I can plot those points as well, 1/2, 1, 2, 3, and negative 4. Now actually, believe it or not, those are the last points that we're going to plot before we go ahead and construct the graph. But we are going to look for some other features. Rational functions often, much of the time, will have vertical asymptotes. Locate the vertical asymptotes by factoring the denominator and setting each factor equal to 0. So just like in step 2, to find the x-intercepts, you factor the numerator. In step 3, you factor the denominator. Now the denominator is nice. It's a difference of 2 squares, so we know that that will factor as x plus 2, x minus 2, and setting the 2 factors equal to 0, we get negative 2 and positive 2. At these values of x, there will be vertical asymptotes. They will be vertical lines at negative 2 and 2, and I'm going to draw those as dotted lines, indicating that they are not part of the graph, but that the graph, once I draw it, will approach these lines, getting closer and closer to them. So we know the x and y intercepts and the vertical asymptotes. Step 4, locate any horizontal asymptotes. Now this rule is a good deal more complicated, and it focuses on the degree of the numerator and the degree of the denominator. The degree of a polynomial is simply the highest exponent on a variable in the polynomial. So the degree of the numerator here is 2, and the degree of the denominator is also 2. Now we look at some different issues. If the degree of the numerator is less than the degree of the denominator, the x-axis is the horizontal asymptote. That doesn't happen this time. There are plenty of examples where that will happen, so we know that this is not the case. The horizontal asymptote is not the x-axis. If the degree of the numerator is equal to the degree of the denominator, and that's true here, and if a is the leading coefficient of the numerator and b is the leading coefficient of the denominator, the horizontal asymptote occurs at y equal a over b. What you do is you make a fraction of the leading coefficient of the numerator over the leading coefficient of the denominator, and that tells you there's a horizontal asymptote at y equal 2. That will be the case for this polynomial. There is a third option. If the degree of the numerator is greater than the degree of the denominator, then there is not a horizontal asymptote. And we'll probably approach that in an example like that in a different video, because what that might look like will again vary. But that's not a problem for this one. We know that in this function, we have a horizontal asymptote at 2, and I'm going to draw that in as a dotted line, again representing a line that the graph will approach, getting closer and closer to, particularly as you go to the left and you go to the right. So that's going to give me some structure to the graph as well. Now we're going to focus our attention back at the x-intercepts. We want to know what the behavior of the graph is at the x-intercept. As a graph hits the x-intercept, it can do one of two things. The graph can pass through the x-axis, which would look sort of like a line, or it can touch the x-axis, which would look sort of like a parabola. Which is which depends on the multiplicity of the x-intercept. The multiplicity of an x-intercept is the number of times it occurs, and also goes back to the power on the factor when the numerator is factored. If I look at both of the factors in the numerator of this polynomial, they are raised to the power of 1. That means that both factors have multiplicity 1, and both x-intercepts have multiplicity 1. And what that tells me is that at both of those intercepts, the graph passes through the x-axis, again, at both intercepts. It won't touch the graph and bounce off it like a parabola. It will pass through. We'll see what that looks like momentarily. So we'll remember that for now. One more ingredient before we have enough to draw the graph, and that's to consider the behavior of the graph near the vertical asymptotes. If the multiplicity of the vertical asymptote is odd, the branches of the graph near that vertical asymptote will go in opposite directions. What do I mean by that? Well, when you have a vertical asymptote and you look at the branches of the graph to the left and the right of that asymptote, they could potentially go in opposite directions, where one branch is heading towards positive infinity and the other one is headed for negative infinity. Or the two branches can go in the same direction, where perhaps one of them, well, perhaps both of them are going towards positive infinity as the branches approach the vertical asymptote, or maybe they might both approach negative infinity. Which one of these two scenarios will happen will depend on the multiplicity of the vertical asymptote. By multiplicity, I'm considering much like I did with x-intercepts. Look at the exponents on the factors in the denominator that result in the vertical asymptotes. Notice that both of those exponents are 1 and 1 is odd. So that's going to tell me that as as I construct the graph and as I approach either one of the vertical asymptotes, the branches will go in opposite directions, more like this, not like that. Believe it or not, that is then enough to go ahead and sketch the graph. Remembering the facts that we have and what we've already plotted, we can sketch the graph. Here's a nice hint. Begin with the y-intercept if you have one, because if you do, that might very well be enough to figure out the complete graph without plotting any additional points. You do have some x-intercepts that you know you're going to have to hit as well. So that may be enough. It may be necessary to plot 1 or 2 additional points if you're a little confused by the behavior, but let's try not to. Now, one note before I jump in and do this. A graph of a rational function will never cross its vertical asymptotes, but it may cross its horizontal asymptotes, just not at values of x that are large in absolute value. By large, I mean heading off towards positive infinity or heading off towards negative infinity. In the middle of the graph, it is potentially possible that a graph may cross its horizontal asymptote. So, at this point, we get very creative, and this is very artistic. I am going to start, like I suggest, at the y-intercept, which is at 1. As I look to the left of that graph, notice that I've got a vertical asymptote 2 units to the left of it, and that's a line that I need to approach. And we might wonder, well, will I approach that vertical asymptote going down? And the reason we can know that doesn't happen is because if the graph moved down as you move to the left, you would cross the x-intercept again, and there would have been another x-intercept. You would pass through the x-axis again, and that means there would have been another x-intercept. That can't happen. So that must mean that the graph is approaching positive infinity as we hit that, as we get close to the x-intercept, the vertical asymptote at -2. We know we're going to pass through the x-axis, and by the way, the y-axis, and by the way, the x-axis, the y-intercept and the x-intercept. And as we move closer to the asymptote, the next vertical asymptote at 2, we can see that that must be going down. Now, what about the graph when we're looking to the left of the vertical asymptote at -2 or to the right of the vertical asymptote at +2? What happens to the graph there? Well, recall that we said that as we approach the either vertical asymptote, the 2 branches are going in opposite directions. So that tells me that as I look just to the left of the vertical asymptote at x equal -2, my graph is going to have to go sort of like this. I will need to pass through that x-intercept. And because I have, and as I hit that point, remember that as I hit the x-axis and x-intercepts on this graph, I always do pass through the axis. And then I would head off this way and approach, but no longer touch the horizontal asymptote. So that's really good. Now we might look over here to the right side of x equal 2, and we might think, oh my God, there's no points over there to graph at all. But remembering that, 2 things actually, the behavior of the graph near the vertical asymptote at x equal 2 is such that the branches are going in opposite directions. So this means that this graph will have to be coming from positive infinity, coming down and approaching the horizontal asymptote. Another reason why we know it isn't down below, like here, I'm going to draw this quickly and then erase it, is if it were down here, you'd have another x-intercept. So we know that that can't happen. We'll erase that quickly. And if we look at this, we see that we now have the entire graph. We only plotted 3 points and the vertical and horizontal asymptotes and thought about what they were. Well, just to kind of check our work, I also sketched this graph on a computer program known as Desmos. So let's take a quick look. Take a look at this graph and then look at the result, and I think you'll see that the computer-generated result does exactly what we were thinking of. You can see in here the vertical asymptote at 2 and at -2. Pretty clear there. And a horizontal asymptote at 2 as well. You can see that. And you do have the x and y intercepts exactly where we'd plotted them before, so I think that worked out pretty well. Now, it's important to do a lot of different practice examples when you're graphing rational functions, because as subtle things happen in the equation, the graph can change quite dramatically, and you'll get some really elaborate shapes. But I hope that is a good first start.